Okay, now that we know polar form or trigonometric form, the idea is why? Why do we need another way of writing and getting used to another way of expressing complex numbers? And the answer is in this kind of long title. These operations are much easier to carry out using polar form. And let's see why. So I'm going to write the first part, in fact, as a theorem. So here's the theorem. It's going to have two parts. So suppose we have two complex numbers written in polar form. So Z1 is going to be R1 CIS of theta 1, cis theta 1. So this is its argument, and this is its modulus. And Z2 is R2 times CIS theta 2. Two complex numbers written in polar form. Then, 1, multiplying them, Z1 times Z2, is just multiplying the moduli, R1 times R2, and adding the angles, the arguments. Very easy. We'll do an example in a minute. And part 2, remember that division was kind of annoying, in fact, in algebraic form, right? We had to multiply top and bottom by the complex conjugate of the bottom, or we even wrote it as a sophisticated formula, right? Z over W was ZW bar over W modulus squared. It was kind of weird. Here it's very easy. Z1 divided by Z2 is just R1 divided by R2. You divide the moduli and you subtract the arguments. Very easy, very easy. So what I want to do is first give an example and then maybe prove at least one of them and see that these are in fact useful facts and not hard to see. So first of all, here's an example. So suppose you want to take 1 plus root 3 of I and divide it by minus 3I. So we know how to do it in regular or algebraic form. You can even do it and see that we get the same answer. Let's see how we do it using polar form. So in order to use polar form, we have to first convert to polar form. And these are precisely two examples that we did in the previous lesson. So this 1 plus root 3i is 2 CIS 60, and minus 3i was 3 CIS 270. So these are these two numbers in polar form. You could say that doing this is also requiring some work, and that's true. So if you want to do it using that theorem and your starting point is algebraic form, then it's not completely clear that it saves you a lot of work. Okay? But the idea is that if you're going to do these things, you should to start with work in polar form. Okay. So now how do we divide them? We divide the moduli, 2 over 3, and we subtract the angles, 60 minus 270. So the actual division is very, very simple. One step, nothing to think, no rough calculations to do. So we get 2/3 CIS of minus 210. You could stop here. You could, if you want, rewrite minus. I'm going to make this very long because I'm exhibiting some other kind of things that you may want to think about or sometimes do. So I'll just throw them all into this example. So minus 210. Remember, we're always thinking of the argument, counting it from the positive x-axis, just like we do in trig. So minus 210 going clockwise, minus 210 is the same as going counterclockwise, the regular way, to 360 minus this, so to 150. So this is another way of writing the same number. Okay, does everybody agree? And these two angles are the same in terms of, remember we said that we think of the argument as a set of angles that differ by multiples of 2 pi, of 360 degrees. If you started in algebraic form, you may want to convert back to algebraic form, and that we also know how to do. So let's rewrite this as 2/3 cosine of 150 plus I sine of 150. And this equals, so cosine of 150 is the x value, so it's going to be minus the cosine of 30, so it's minus root 3 over 2 plus I times 2/3 from out here, and then sine of 150, which is the y value, so it's precisely the same as sine of 30, so it's just 1/2. And now we can cancel some stuff out here, so we have minus root 3 over 3, or 1 over root 3, whatever way you want to write it, doesn't matter, plus 1 over 3i. Okay? And one more thing you can do is multiply this by minus 3i and see that you get this. See that we indeed got the quotient. Okay? So the point is that if you want to go from an algebraic representation, convert to polar, do the division in polar, and convert back, it's going to be a bit of work. But if you start in polar form and want to divide, that's it, you're done. It's just a very simple one move. Okay? Let's prove a bit. Let's prove, for example, the first part of the theorem. Remember, the first part was that the product of two complex numbers is the product of the moduli times the cosine plus I sine of the sum of the arguments. Let's prove this. So how do we prove something like this? So proof of, we called it 1. How do we prove it? We take the two numbers and carry out the multiplication. So z1 times z2 equals. So it's r1, I'm going to spell it out in full detail, cosine of theta 1 plus I sine of theta 1 times r2 cosine of theta 2 plus I sine of theta 2. So this equals, r1 and r2 already meet multiplicatively, that's easy. But now we have these two, think of them as algebraic expressions, and I'm multiplying them, so I'm going to get each of these two terms to meet each of these two terms, right? So cosine of theta 1 times cosine of theta 2, let's move it a bit backwards so we have enough space. So it's r1, r2 times cosine theta 1 times cosine of theta 2. And where else do we get the real part when we multiply the two expressions that have I in them? I squared is -1, so we're going to get a minus, and then here the sine and the sine meet. So sine of theta 1, sine of theta 2. Right? Plus, so all of this is multiplied by r1, r2. And now we have cosine of theta 1 times I sine of theta 2. So cosine theta 1 sine theta 2 plus, and I'm going to write the other expression, and there's going to be an I out here, and then this is closing these parentheses. And the other one that I have is I sine of theta 1 times cosine of theta 2. Right? A bit long, but entirely straightforward. I didn't do anything, I didn't pull any tricks out of my sleeve, right? Completely straightforward. And now, can you guess how we would proceed? Very good. These are trigonometric identities, well-known trigonometric identities, you may not remember all of them by heart. I don't, and I don't recommend to try to remember all the trig identities by heart. But when you see an expression like this, you should recognize that there is an identity for it, and then go look it up. And I'm going to look it up here in my notes. And what it is R1, R2. This is the expression for the cosine of a sum, cosine of theta 1 plus theta 2, plus I, and this is precisely the identity for sine of a sum, sine of theta 1 plus theta 2. That's what we get. And this, in turn, is just shorthand, can be written in the abbreviated notation is R1, R2, CIS, theta 1 plus theta 2. Okay, so this is the proof. We just proved part 1 of the theorem that the product of two complex numbers is the product of their moduli times cosine plus I sine, the sum of the arguments. Okay, good. And we did an example. And if you think a minute, we know the product of two numbers, we may as well throw in a third, right? So we know how to do z1 times z2 times z3. It's going to be r1 times r2 times r3, and then the sum of the three arguments. And by simple induction, or you can just observe it trivially, we get the following formula, which is called de Moivre's formula, named after the mathematician de Moivre. So here it is. So it's a theorem, very easy to prove, attributed to de Moivre. And it says the following. If you take a complex number and raise it to the power n, now doing this in algebraic form could be somewhat tedious, could be not too much fun, unless you like doing stuff like this, and then it would be fun. But in trigonometric form, in polar form, it's extremely easy. It's just r to the power n, and then cosine plus I sine of n times theta. Very elegant and very easy to carry out. Okay, so this is de Moivre's theorem. Let's do an example. So example, suppose we want to calculate root 3 plus 1i to the power 15. So I need a volunteer. Yes, okay, good. So what you're going to do, you're going to not listen to us, ignore us completely, take your paper and start doing this. So multiply this times itself 15 times, tell us when you're done, and tell us if you had fun, and also we'll check if you got the correct answer. Okay? Good. So, no, of course it's a joke. You don't have to do it, unless you want to. I mean, it's good practice, but let's do it the easy way. Let's be lazy. If we have this very elegant theorem, the proof is obvious, right? It's easy induction on the multiplication theorem that we just had. So how do we do this? Well, if we want to do it using polar form, we're going to have to convert to polar form. So what is the polar form? So r is the root. We always get the same thing, right? These examples are not very interestingly chosen. So it's root 3 squared plus 1 squared. So it's 2, as it was in many of the previous examples. So that's r. And theta is arctan of b over a of 1 over root 3, which gives 30 degrees. And in this case, it is the correct answer because this number lies in the first quadrant. Okay, remember we mentioned that there's a little delicate issue here. So this number is just 2 cis 30 raised to the power 15. And by de Moivre's formula, it's 2 to the power 15 times cis of 15 times 30. This is a little multiplication sign here, right? It's not 1,530, it's the product. 2 to the power 15, you could go ahead and calculate it, but it's perfectly fine to just leave it like that, okay? It's not an enormous number, right? 2 to the 10 is something like 2,000, I think, but you don't really need to find the exactly what it is. This is fine, this is sufficient. 15 times 30 is 450, right? And 450 is equivalent to what? In terms of the argument, which angle between 0 and 2 pi, or 0 and 360, would this be equivalent to? Right, 90 degrees. So this is 2 to the power 15 CIS 90, and it gets even nicer. Here it's 30 degrees. Because what is cosine of 90 plus I sine of 90? What does 90 degrees correspond to? Right, it's just good old I, right? Cosine of 90 degrees is 0, sine of 90 degrees is 1. So this is just a way of writing 2 to the power 15 I. And it's even back in algebraic form. So root 3 plus I to the power 15 is the same as 2 to the power 15 times I. It's a purely imaginary number with no real part. So what did you get? Good! That was pretty quick. So you did all 15 of them? Ah, you're kidding me back. Good. Good. You win. Okay. Is it clear? Is this procedure clear? Okay, it's not difficult. I think it's very, very, in fact, elegant. It's quite neat. Quite neat, this de Moivre's formula. And remember, we mentioned that when complex numbers were first introduced, they were treated rather suspiciously, rather with kind of, nah, these are imaginary things, okay? And they were introduced in terms of solving equations. And when de Moivre came along and showed their relation to trig, and you can even go ahead and prove some trig identities using complex numbers. I don't have time to show you examples of that now, but there's very elegant proofs, for example, for cosine of the trig identity for cosine of 3 theta, or sine of 3 theta, can easily be derived using complex numbers in these formulas. Okay, so that kind of convinced more people that these complex numbers are things that are worth considering. Okay, they're very, very natural things to think of. Okay, okay. So one last thing regarding complex numbers is roots. So we know how to do powers. How do we do roots? And here we come across something kind of interesting. So I want to first make a little, let's say, intuitive observation. So raising to some power, what it does to the number on the plane, what it does geometrically, well, it stretches the distance from the origin, or shrinks it, depending on whether r is less than or greater than 1. Okay, so the modulus just expands or shrinks by power n. But the argument actually rotates. Okay, so when you raise something to the power 15, you take the angle and you multiply. You rotate it by 15 times the original angle. Okay, so multiplying kind of corresponds to rotating and stretching, but also rotating. Okay, so taking roots, which is the opposite operation to raising to powers, if you take a number and ask what are its roots, they're going to be numbers that when you raise them to that power of the root you're taking, they rotated until they got to that point. I don't know if this is completely clear what I said. Let's do an example. So let's write a definition first. Let's formalize it a bit. An nth root of a number z, a complex number, of z which belongs to the complex number, is a w, is a number, another complex number, such that, that's the abbreviation, such that w to the power n equals z, right? This is just like we define for real numbers or for integers or whatever. So here's an example. And what's going to turn out is that each number z, if you ask what are the roots, the third roots of z, there are going to be 3 of them. And what are the roots, the fifth roots of z, numbers that when you raise them to degree 5 you get z, there are going to be 5 of them. Okay, that's the phenomena we're going to see. So example, suppose, let's start with the w. W equals, let's say 1, so it's just on the unit circle, it has a modulus of 1. Cis, what did I take here? 45. This is w. So z is going to be w to the power 4. I'm going to raise w to the power 4. I know how to do that by de Moivre. So the radius is going to stay 1, the modulus. It's still going to live on the unit circle. And the angle, the argument, is going to be 4 times 45, which is 180. Do you agree? Okay, so 1 cis 180. If you think of the picture, everything here lives on the unit circle. Let's draw the unit circle for reference. So everything here lives on the unit circle. W was with 45 degrees, so this is W, lives on the unit circle, and it has an angle of 45 degrees. And when I raise it to the power 4, I do 1, 2, 3, right? Or 1, 2, 3, 4. So this is what I get. This is z. Do you agree? Okay, this is what we just wrote here. But if you think of this a bit more, if you start with, let's say, this number here, it also has a modulus of 1. It's on the unit circle, and it corresponds to the angle 135. What's going to happen when I raise this number by 4? I'm going to take 135 and multiply it by 4. So 1, 2, 3, 4. I'm going to land back precisely at z. 135 times 4. You can do it, just do the arithmetic. So it's what? 400, 520, 540. And 540 corresponds between 0 and 2 pi, precisely to 180. Okay? So this number is also a number that when raised to the power 4, you get the same z. Okay? And so are this number and this number. Okay? So this number here is 1 cis, what? 180, 225. And this number here is 1 cis 315. Okay? And all 4 of these, when raised to the power 4, do it. Do it if you're feeling a bit, how do you know? Do it. Do the calculation. Multiply this by 4. 1 is just going to stay 1. Multiply this by 4, and then take the representative between 0 and 180. You'll land here. And 360. You'll land here. Okay? So all these 4 numbers, when raised to the power 4, give you z. So let's call this one W0, and let's call this one W1, and W2, and W3. And then let's write here, so W0 is this, Z equals W0 to the power 4 is that, but W1 to the power 4 equals W2 to the power 4 equals W3 to the power 4, and all of them equal Z. So Z has 4 separate roots of degree 4. Okay, so 4 fourth roots. Okay, and this is going to be the picture always. Okay, so let me write what I mean by always. When you take a number Z, so I think the idea is not too complicated to grasp. What's a bit challenging is what the way I'm going to express it right now, the way I'm going to write it. But it's also something that you just, as are many things, just something that you have to get used to. Okay, so in general, for every Z, complex number Z, or let's write it in polar form, for every Z, there are n roots of order n. They all sit on a circle of radius, so they all have R equals, or have modulus, R is the modulus of Z, they all have modulus, which is the nth root of this R, right? Because when you raise this to the power n, you get precisely R. And their arguments, just like in the example we did, are going to be theta divided by n, and then start multiplying it until you get n times. So it's theta divided by n, or let's say, let's just write, and arguments theta plus 360 degrees times k divided by n. That's it. That's what I wanted to see. Okay, so what do I mean by times k? K is going to be 0, 1, 2, all the way up to n minus 1. Okay, so when I take k to be 0, it's just theta over n. So when theta was 180 degrees in the example, theta over 4 was 45 degrees. That was the first number which raised to the power 4 gave Z in that example. When k equals 1, I get theta plus 360 divided by n. In the example, theta was 180 plus 360, 540, divided by 4. That's the 135. That was W1 in that example. When k equals 2, I get theta, plus theta was 180, the argument of Z, plus 2 times 360, so plus 720. Together it's 900. Divided by 4, 225. That was the third root. Okay? And when k equals 3, I would get the fourth root, which was 315. And when n is 4, you just stop at 3, right? You go all the way to n minus 1. Okay? So one other way of writing this, the nth root of Z is the nth root of R times cosine plus I sine of theta plus 360 degrees times k divided by n And it's a set of all these numbers where k can be 0, 1, all the way up to n minus 1. Okay, so the nth root of z, it's not just one of them. Okay, there are n of them from 0 to n minus 1. That gives you n distinct numbers, and this is what they are. Okay, so sometimes seeing this is a bit confusing and maybe even frightening, but think what we did in the example. That's precisely what we did. Okay. Another example, maybe one last example, just to. And I'm going to mention one more observation that would wrap up our discussion of complex numbers, or at least in these lectures. So, example, find all roots of unity. So this is terminology. Roots of unity means roots of the number 1. That's what they're called. They have a name, the roots of unity. So the roots of the number 1 of order 6. So find all the numbers that when you raise them to the power 6, you get 1. So what I want to do is use that expression that we wrote at the bottom of the previous board with cosine plus I sine of theta plus 360 degrees times k divided by n. So let's write it. The sixth root of 1 is, well, the sixth root of the modulus of 1, which is 1, so that contributes nothing. They're all going to sit on the unit circle, right? And then we're going to have the angles, cosine plus I sine of, one has an angle 0, so it's 0 plus 360 degrees times k divided by 6. So these are the numbers that I'm going to get, where k ranges from 0 to 6 minus 1. There are going to be 6 of them. And now all that you have to do is start plugging in these 6 different values of k, and you get your answers. So the first one is going to be cosine plus I sine of 0, which is just the number 0. Sorry, that was stupid. What is cosine plus I sine of 0? Right, it's the number 1. Cosine of 0 is 1, plus I sine of 0 is 0. So plus 0i. So this is just 1. 1 to the power 6 is indeed 1. So 1 is a root of unity. Okay. The next one is going to be cosine plus I sine of 360 times 1 divided by 6. So cosine plus I sine of 60 degrees. So cosine of 60 degrees plus I sine of 60 degrees. So what we get is 1/2 cosine of 60 degrees plus root 3 over 2 sine of 60 degrees I. The next one, 720 over 6. So it's cosine plus I sine of 120. So it's minus 1/2 plus root 3 over 2i. And let me write quickly the other 3. Cosine plus I sine of 180, which is negative 1. Negative 1 to the power 6 is 1. Right? It's also a root in this sense, a root of unity. And the last two, minus 1/2 minus root 3 over 2i, and cosine plus I sine of 300 degrees, which is 1/2 minus root 3 over 2i. And just a remark, reflecting on this for just another moment, you can observe that the sum of these 6 numbers is 0. Okay, so 1 minus 1 cancel out, and then we have 1/2 minus 1/2 minus 1/2 plus 1/2 plus root 3 over 2i plus another 1, minus 1, and minus 1. So there's sum. The sum of all 6 is 0. Do you see that? Okay? And this is, in fact, a general phenomenon. So let's write it, and that's where we'll end and take our break. So the sum of the nth roots of unity is always 0. So we can call it a theorem. The sum of the nth roots of unity is 0, and this is true for any n. Okay, so if you take n to be 2, for n to be 2, then what are the roots of unity of order 2? They're minus 1 and 1, and their sum is 0. Okay, so for any n greater than for n greater than or equal to 2. Okay, so if you take all 4, remember the 4 numbers that we had that we called W0, W1, W2, W3. I did it backwards for you guys, right? So W0, W1, W2, and W3. Okay, those were not roots of unity, right? Okay, so try to prove this. Try to prove this. Try to prove. It's not hard. I'll give you a hint. Give them names. Give them names. Call them W0, W1, W2, and so forth, all the way up to Wn minus 1, and show that they're in fact a geometric sequence. Okay, that you get one from the other by multiplying by a fixed ratio. Okay, and then you know the sum for a geometric sequence. For a finite geometric sequence, and you get precisely that. Okay, so very easy. Try to prove. Hint: geometric sequence. Okay, so this is just a bit of playing around with this stuff. Okay, I wish I had time. I have here some very nice little things, but maybe you'll encounter them in discussions or in tutorials. But we're gonna stop here our discussion of the complex numbers. It is important, and I do want to emphasize, if you don't have the working ability with these numbers, if you haven't developed it yet, either because you just haven't, even if you've seen them before, or if they're completely new to you, it is important to do so, and do it now, okay? Take some time to really practice a lot until you feel that you're good at transferring from polar form to algebraic form, and carrying out addition and multiplication in both forms, and doing division in both forms, and taking roots and raising to powers, and all of that requires practice, as does almost anything, but in particular, this is going to be very fundamental in this course. We're going to work a lot with complex numbers. They're part of our world now, and if you're not used to them, think of it. You're going to try to do higher math without knowing the very basic numbers you're working with. So please take time and practice. Okay.